Welcome back. I trust you were able to answer those questions on equivalent dose. I'm sure you found that they were quite simple and easy to do. And now we move on to effective dose. So what is effective dose? Different tissues and organs are affected differently by radiation. Pretty simple, right? So for example, lung tissue is more likely to be affected by radiation than is the skin. In order to account for different sensitivities, the equivalent dose is multiplied by a tissue weighting factor this time, and then the resulting unit is referred to as the effective dose. The effective dose is also given in the unit called sievert or millisievert. The effective dose limiting system is a way of understanding the various risks of cancer and hereditary effects to the tissues or the organs that were exposed to the radiation. Now, because various tissues and organs do not have the same degree of sensitivity, we have to represent this somehow, and this is done in this table here to the right. You can see we're using tissue weighting factors to distinguish or differentiate between which organ is more sensitive than the other. So when you are taking an X-ray and a part of the body is exposed to medical radiation, the biological damage will depend on the exposed organ and that organ's sensitivity to the X radiation. The International Commission on Radiological Protection, once again the ICRP, has introduced the concept of a tissue weighting factor. In summary, the concept of radiation exposure and the associated risk of the radiation-induced malignancy is the basis of the effective dose-limiting system. And accounting for tissue weighting factors is important because various tissues and organs do not have the same degree of sensitivity. Now, because effective dose accounts for different types of ionizing radiation's effects on different types of tissues, each with their own unique radiosensitivity to ionizing radiation, the effective dose is essentially the sum of all of these factors. So effective dose takes the absorbed dose in gray, and it multiplies this value by the radiation weighting factor. Let's say you used X-ray, so you multiply that by 1. And then you look at the tissue that you're dealing with, and then you use the tissue weighting factor for that type of tissue that you expose to radiation. So the effective dose looks at each organ's sensitivity to developing cancer from radiation exposure. Now, although effective dose best reflects a patient's overall exposure to radiation, organ-specific dose may be more appropriate for estimating lifetime cancer risk for non-uniform exposures, such as a CT scan. For example, if the patient undergoes an imaging study that radiates only the breast, her risk of cancer from that examination will primarily reflect her increase in breast cancer. So effective dose and equivalent dose are equally as important. However, that being said, I want you to remember that when looking at the effective dose limiting system, the dose limits set out by the ICRP, this does not apply to medical exposures. It is only for occupational and non-occupational, the public, and does not once again include medical exposures like the example that I just provided. On that note, I want you to try and solve the problem in the slide here to the right. You're going to calculate the effective dose on a patient that has undergone a CT scan of the chest. And the formula is there for you to calculate this effective radiation dose, and that is the absorbed dose multiplied by the radiation weighting factor and multiplied by the tissue weighting factor to come to your answer. So what is the rationale for setting occupational dose limits? Well, occupational risk to ourselves are generally very low, and we practice safely and our job is considered safe. Now the risk is estimated to be 2.5% chance of fatal accident over an entire career. Adherence to the occupational dose effective limiting system helps prevent any harmful biological effects of radiation exposure. As you can see here below, the ICRP recommends that we receive an effective dose of 20 millisievert per year, averaged over a 5-year period, no more than 50 in 1 year. And an annual equivalent dose to the lens of the eye is 20 millisievert. The skin is 500 and the hands and feet are 500. These are values that you should learn and know. When it comes to yourselves as students, though, the effective dose to yourselves should be no more than 6 millisievert according to Hamad Medical Corporation, but according to ICRP guidelines, you should be following the same regulations as the public and should receive 1 millisievert of radiation per year. So who does occupational dose limit apply to? It applies to any person who is exposed to ionizing radiation as a direct and a necessary condition for their employment, and therefore they are considered occupationally exposed. Occupational exposure or dose limits are specified for both the whole body dose and for exposure to certain tissues and organs in the body, as you could see in the previous slide. So once again, here are some dose limits in a table format for occupational exposure. And these are the dose limits recommended for public exposure. The ICRP makes recommendations on both the occupational and the public dose limits, and adherence to the occupational and non-occupational effective dose limits does help prevent harmful biological effects of radiation exposure. So what is an action limit? An action limit is put in place usually by the RSO, the Radiation Safety Officer, or the Radiation Protection Officer. They use action limits when or to prevent certain radiation doses from being exceeded. In a well-run facility like CNAQ, the radiographers and the students should never go above the maximum level or never get to the action limit. If the action limit is exceeded, it should be investigated by the RSO, and the relevant authorities should be involved as well and should be notified. So, for example, if you're working at Hamad Hospital and your dose levels are quite high and you've reached the action limit, Hamad Hospital will be notified, and the Ministry of Municipality and Environment that is involved in the radiation safety within the country, they get notified as well. And then what happens after that is we assess the possible reason for the radiation dose or the increase in radiation dose, and an investigation is conducted to mitigate any future issues or incidents with high doses in the future. The reason for unusual readings is often TLD badges were put in the clothes dryer accidentally. It was left attached to your lab coat, and you forgot about it, and you put your lab coat in the washing machine and then in the dryer, and it affected your reading. Another common issue here in Qatar is you may have left your TLD badge in your vehicle on your way home from clinical. You took your lab coat off, you put your TLD badge in the cubby of your car or on the dashboard, you forgot about it, and the next morning you're on your way to work again and you notice it and it's been exposed to about 50 degrees of heat. So this will definitely affect your reading as well. But in most instances, it's just a simple error and can be fixed easily. There's never been a case where there was reason for concern. So now that you have gained some knowledge on absorbed dose, equivalent dose, and effective dose, and biological effects of radiation, I want you to try and answer this question. So why did Bunny B die? Bunny A and Bunny D have both received the same amount of radiation exposure. Bunny B has received 2 sievert or 200 rads of radiation, and Bunny A has received 2 sievert or 200 rads of radiation. Yet Bunny B does not survive. Why is that? So in summary, different biological threats posed by different types of ionizing radiation must be taken into consideration even when the absorbed dose is the same. Serious radiation-induced responses may be classified as having either deterministic or stochastic effects, and deterministic effects are those biological effects of ionizing radiation that have a threshold dose. So when they reach that threshold, the severity of biological damage increases as the dose increases, whereas stochastic effects are non-threshold. They occur randomly. There is a probability or a chance of the occurrence of such an effect occurring, and they usually link to cancer. Bunny A survived because he was only exposed to X-ray, and X-ray is minimally damaging. It's minimally ionizing. It travels at the speed of light, and it moves through the substance quite quickly, whereas alpha has a higher radiation weighting factor, and it has a higher mass, and for that reason, when it does penetrate the body, it is more harmful. When alpha does damage the body, it is more difficult to repair. resulting in a lower survival rate, and therefore Bunny B did not survive. Remember, alpha is emitted during the decay of radionuclides like uranium and radium, which are very toxic substances. Now, I have included several review questions for you to go through to determine whether you have a good understanding of the concepts that we discussed in this PowerPoint. So to conclude our lesson, I would like you to try and answer those questions now as soon as you are done with this lecture. And then I want you to note the resources as well in this presentation. You can spend some time, because you do have some time here, looking into these resources and seeing what they're all about. ICRP recommendations are available online, and it is accessible to the public at no charge. All you have to do is sign up. So on that note, we'll end our lesson, and we'll continue again real soon. Have a good afternoon, guys.